Welcome.
Well, thank you very much for inviting me to give me this opportunity to be here for the second time at Field Institute. I was here more than 10 years ago, and to revisit a problem with old techniques and leading to new things and open things that you'll see that are challenges. I am just so in order to prove here what is necessary to share here, what's happening was there is here. So you read my abstract, so but it's appeared. So I think it should be here. What should I share? I'm sharing. I'm tired.
Yes, you are.
So it's not my problem. It's your problem. Okay. Thank you. So, okay. So since this workshop in free boundaries, life science and fluids, I tried to find some free boundary problem that could have some interest, maybe in biology, in chemistry, in reaction diffusion. You'll see. And the main idea is, okay, you know better than me what is a reaction diffusion system, and you have the reaction on the right-hand side. And the idea is, since the aim is to consider a kind of a change in the coefficients that are involved in two phases. The phase, I mean, the free boundary is the level set where the two components U and V are equal. This is a priori free boundary. You don't know where this is this level set. And the concept is, suppose that you have any reaction diffusion system where one phase, say U strictly larger than V, you have one coefficient, one class of coefficients. In the other zone, you have different, and they may vary discontinuously because they jump from one phase to the next phase. Of course, the level set can be a set, not really a boundary. It can be more complicated. In fact, this kind of problem has been called two-phase obstacle problem, where there is no really an obstacle here. The fact is that if you take the positive, I mean, the positive difference of this is one phase, negative the other one. In a certain sense, you can see not really an obstacle, but the level set similar to the free boundary in the contact obstacle problem. And this is the reason of the terminology. In fact, the problem has been analyzed and studied in the homogeneous case where just one equation, scalar problem, just a scalar problem, when V is just 0, for instance. My aim is to arrive to this couple system where I have here a kind of maybe bit operator, or this S means you can also handle this with certain classes of fractional Laplacian, so in Gallardo type or in the Rodrigues fractional derivatives, which in Hilbertian case are essentially the same. Of course, there are the issue about the boundary conditions. And boundary conditions can be more or less complicated in the fractional framework, but in any case, I will take just Dirichlet homogeneous to simplify. I'm not focused on the boundary conditions, but what happens in the two-phase bulk. So, in order to study this, this is basically a characteristic function. So, one, if a point is in this region, 0 in the complement. Okay. However, I'm not able to solve in general the problem with characteristic functions. I will introduce a quasi-characteristic function. So, but in order to solve the, so of course there are certain hypotheses that I'm going not to be optimal. So the characteristic functions are as usual here, this notation. This phi plus or minus in general, they can depend on U and V. To start with, I will only assume that they depend on X and T. Omega is my bounded open domain in RD. T is time, as usual. So I take Dirichlet to simplify. And I take no negative coefficients here because I want to use monotonicity methods for the uniqueness at least, and for some comparison if necessary. But I am also simplifying, telling that these are bounded functions. They can be more general cases. In the end, I say something about it. And I'm using these notations because I want some freedom to choose these coefficients. The phi plus and minus. Plus means this plus, this corresponds to minus, and then they change. This is the same than this, and this is the same than this. And of course, these functions can be also depending on u and v, but let's start simply by just assuming given functions for the moment. And I'm going to start just with the scalar problem, to study deeply the scalar problem, and then to see how can we do it, the system.
Can you suggest to us some interpretations of variables so we have some solution to the problem? Or some application?
Okay, take the Predator system. I don't know if there exists any real model where you change one coefficient of the. You see, say if the population is larger than the other one, but you can more generally use here some other function if you like. That means suppose that the density of one population is larger than some threshold, which may be the density of the other population. And if you are above that threshold, you have one kind of reaction. If you are below, you have another kind of reaction, and this change discontinuously. There exists this kind of systems. I don't know. If you can find one new one, I shall be happy. But I'm just taking this. Of course, you can think about reaction diffusion also in chemistry, for instance. Any kind of, or just take just one equation, okay, and say that you have a reaction that depends on some threshold, which can be given. Because when I consider just the scalar case, just the first equation, I suppose that v is a given function. And in fact, I can solve this problem just with v in L2, which is very general. So this is I'm speaking about a general analysis approach to these kind of problems, to see they are possible. If they are useful in some physical situation, I don't know. I don't claim they are useful. I hope so.
So anyhow, you had in mind that U is the density of predators?
For instance, one possibility. But it can be a chemical reaction. You think of other things if you like, okay? I'm just thinking in general. And I believe this can happen. In principle, it can happen. In physical situation, I'm not a physicist, so I cannot guarantee that. I don't know. Okay, so, well, as I told you, the problem is that this level set where the two functions are equal, or where the u attains the threshold v, which can be a priori given, can be a non-empty, a set of measure, positive measure, not really a boundary, but a set. And in fact, what you can obtain is relaxing this characteristic function by what I call a quasi-characteristic function, which is a function between 0 and 1. And you see that it is 1 if it is in this bigger zone, u bigger than v, it is 1. And it is 0 if it is u strictly smaller than v, because then this is 0 and this must also be 0. So, and in between, in the interface, this quasi-characteristic function can take any value between 0 and 1, okay? And in this way, I am relaxing the formulation of a problem, and I can solve it. And then I will try to find sufficient condition to prove that, in fact, this quasi-characteristic function in certain situations, in non-generate case, can be, according to some assumption on the data, compatibility condition on the data, can be, in fact, the boundary. I don't know nothing about regularity except in a stationary case. I will mention them later. But I will speak about this non-generate case later on. Okay, now think first what I call the local case, the it operator, the it equation on left-hand side. Forget about S. S can be a fractional Laplacian, but essentially the techniques are very easily extended once you have the right functional framework. And I'm not going to spend time with this today. So basically, the first quite general result is that if you give an initial condition in H10, should be HS0, but this is VS, the space for the Laplacian or for the fractal Laplacian. The time derivative also in L2, provided you have U0 in H10. So I'm taking good assumptions. So there exists a unique U, and there exists a key bigger, a key smaller. I mean, there is this in yellow smaller. I mean, there are two quasi-characteristic functions in L infinity. In general, they are not unique. U is unique. In general, Q may not be unique. This sum is unique. Okay, and I'm just giving to start the case where phi plus and minus are just function of x and t. In this case, it is in fact sufficient. They are just L2. Okay, just L2, no negative. These are the assumptions, F L2. So it's a quite general framework. And the existence to this problem, which is a parabolic equation in a certain sense, linear discontinuously through these terms, because these terms are quasi-characteristic functions, and in fact they satisfy these two conditions. Okay, with the bigger and with smaller, and this is what they call the quasi-characteristic functions. Okay, what means a solution? Usually in the variational framework, you multiply by a test function and integrate by parts. Here, this L2 is not necessary. Here is necessary, but in a certain sense, you have here the bilinear form associated with fractal Laplacian, and that's it. Essentially, what you have in the second hand is an L2 term, a priori bounded, so there is no really difficulty to solve this problem, and uniqueness by multiplicity of the key. Why? Because, in fact, well, there are some remarks. First, in particular, we have that, in fact, the Laplacian, or even like Laplacian in the L2 function, because we have this L2, this L2, and this is L2, so this must be L2 almost everywhere as well. And in fact, the remark about non-generacy comes exactly from this inequality, because as you see here, this function is smaller or equal than 1, as well as this one. So you can bound this by these two values, which means that if you give a threshold V, a priori V was just L2, but it can be more regular. And this V has also this time derivative and Laplacian of V in L2. And if you impose that this quantity with V here is all strictly larger than phi plus, so this cannot happen. This violates this, or it violates the other one. It means that, in fact, it cannot exist a set of positive measure for the level set. The level set as in omega t in space-time, Lebesgue negative measure. So if it's 0, this Lebesgue measure, this means that, in fact, the quasi-characteristic functions, they are characteristic functions. So this is a sufficient condition that, in fact, this characteristic function is this, and of course, they are related. One minus the other one, okay, the complementary, because it is, of course, almost everywhere equality. So it makes some sense to use this. Let me just mention about the quasi-stationary case. The stationary case, there is something about the free boundary. In fact, there is all a book by Raltseva, Shengolian, and the third one author, I don't remember now, that studied the case, the equation, they call it with F equals 0 and V equals 0. And in this case, it can happen that, in fact, the situation may be quite complicated. Maybe situations like these. And it may have reasons that can be negative here and can be, so there are possible single possible, and there may be very general situations, very complicated situations in free boundary, even with F equals 0. Of course, you see that non-generacy requires that the F is different from 0. But in any case, even without this kind of singularities, which always can arise, even if the In the stationary case, I just take the stationary case, so no time derivative, no time. So u is just function of x. V is 0 to simplify. If not, it should be more complicated, but it's not impossible. If the f is bounded variation locally, and these functions phi plus and phi minus are also continuous and W1 locally, this means that in fact, under the corresponding stationary, so you just neglect that term with u because it's 0. So if f is strictly larger than phi plus or strictly smaller than minus phi minus, in particular in this open set where this is different from 0, locally the free boundary is in fact, I mean, what this condition BV with this non-degeneracy assumption allow to prove, it was something that I did more than 10 years ago, that in fact this characteristic function is BV. And if it's BV, by the Georgi results, the free boundary is at most a countable union of C1 surfaces, hypersurface, minus a set, possible singular set, which are perimeter 0. The perimeter is, of course, with respect to this characteristic function of this positive set. Okay. This is what is known in most general case for non-negative f, for a different from 0 f in BV. Well, maybe this is a naive interpretation, but let me give you an interpretation. Okay, suppose that you have some kind of f, which is extra things that are coming into the system. And you see, if they are or too negative or too positive, somehow this oblige this region to disappear. Of course, the singularity can remain, but they have 0 measure. Because the reactions, I mean, this extra f term is too large or too small. I mean, this is what this means. If this exists in reality, I don't know. Okay. Okay. Now, what is the procedure to find a solution and is to make an approximation of the basically characteristic function is related to Heaviside function. You just make an approximation with Lipschitz, very simple. 0 for negative values is linearly with slope 1 over epsilon and 1 if it's larger than epsilon. Okay? The problem becomes more regular. You replace what are the discontinuities by this Lipschitz function. And for each epsilon, this is a monotone simple problem. With our assumptions, there is a unique solution with this regularity. And with a priori estimates, which are standard. I mean, I'm not going to take your time. This is a simple exercise to show that it is a priori bounded in L2, the time derivative. Just multiply the equation by time derivative and integrate. The gradients are also bounded in L2 in the local or in the fractional case as well. But of course, in fractional case, you need to take all RD, but it's a technical issue. And by compactness, this is converging strongly and continues with values in L2, so we can pass to the limit. And in fact, you see that these approximations are always between 0 and 1. So you can extract sequence converging weakly star in L infinity to some function which is between 0 and 1. The issue now is to check that in fact they are characteristic function in the sense that I have defined. Yes? No, the V now is given. No, I'm splitting the problem in several steps. Now I give the V just in L2 function. Okay? So V is given. I will come back to variable V later on. V is given, so there is nothing to do with V, just take it there. And you see, this is between 0 and 1, so there's no problem to let go to some sequence to go to limit, and we call this function this way. The functions are here. Now, the argument is we need to show that, in fact, this limit function, so let's do first, the second one is symmetrical in certain sense. I need to show that it's this key is larger than characteristic function of this of the set. So it should be 0 if it's here. So for this, what we do, we just take the product of this, which converges weakly in L infinity star, and this which converges in L2. So this limit, and on the other end, you see if this is as if this is smaller than V, when this is non-negative, non-zero, I mean, non-zero is when this is more than this one, this is always 0. So this is always 0, so the limit is, and on the other end, this goes weakly here, and this goes strongly. So it's very simple. And what this means that we're restricted to this domain. And of course, if V is larger than this, and this is 0, this must be 0. And this is the first part of one of the conditions of the quasi-characteristic function. And second one is more or less similar. A little bit. What you do, you just take the product of the 8 epsilon in this region, and you see that this is also because in this region this is smaller than epsilon, so this limit is 0 when epsilon goes to on one hand. On the other hand, you see that you can write this in this form, and well, I should take this out and split this, and then pass to the limit. See again, this converges weakly, this converges strongly in the whole domain, and then you restrict again to where this set is here. And you see that by the same reason, if this is 0, and if this is larger than this must be 0, which means it must be 1 exactly in this set. And this is the remaining part of the quasi-characteristic condition that we required. So we have this conclusion. And similarly, you see, with similar arguments, we have the second one. So in fact, our limit is something that we expect to obtain. So this makes some sense. In fact, this approximation is a little bit better because there is this property here, this property upstairs here, this property. In fact, this property helps to show that, in fact, in the L infinity values in L2, in supreme with respect to T, and in the energy part, the gradient in L2 norm, are controlled, the square are controlled by epsilon, the L1 norm to the phi plus and phi minus. And this is just taking the difference between the approximated, take the difference between the approximated and limit problem. And I recall you the limit problem is just this equation. Make the difference, and the difference just control, because this disappears. I mean, these terms are controlled by that estimate, and what is necessary to control is this gives the first part, and the second one is given by controlling these terms. And these terms here use that estimate. Of course, there is some argument. I think I can split the arguments, but basically, is again the fact that this is more than epsilon in this region. And then you can use this, and you can do this for the phi plus, and the same for phi minus, and basically you have this a priori estimate, which is useful because it gives you, in terms of u, you do not know anything about the conversion of the quasi-characteristic function. Don't know that. We only know about u, but nevertheless can be already of some use. This approximation. It's a good approximation. Well. Okay, now I was thinking basically to tell you, think about Laplacian, but you can also think about the fractional Laplacian. One way to write the fractional Laplacian is, in fact, maybe I should go now to, this is just, I don't want to spend much time with, is about in fact, everything that I've been said is also possible for this type of non-homogeneous operators. I mean, if they are second order in the classical principal part local. But if you use the Riesz gradient, which is the classical gradient of the convolution of the Riesz potential with the function, which is non-local here. Yes, here the Riesz potential convoluted with the function nu, and you take then derivative. This is the Riesz gradient, the Riesz S gradient, depending as between 0 and 1. And in fact, I forgot to mention, but the nice thing that exists is that in fact the minus S Laplacian can be said as the divergence, the S divergence. I mean, I call it D. Put you here. As I think, did I write? Yeah, I wrote there. In the case dSu. Of course, S equal 1. This is minus divergence of the gradient is minus Laplacian, of course. But the advantage of the Riesz gradient, fractional gradient, is that you can insert here a non-homogeneous matrix. Of course, if you take the Gallardo non-local Gallardo fractional derivative, you replace this by this type of integral, and then use the dSu, dSv with I mean, this is not exactly the right definition, but it's a way to introduce the bilinear form associated with fractional Laplacian. In the Hilbertian framework in L2, they are essentially the same derivatives, but this is just to tell you that, in fact, the fact that you have the advantage with the fractional in ORD, there is an advantage that is the following. You can just take integration by parts in ORD. If phi has compact support and also this vector field the same, you can just make integration by parts in all the with minus. I mean, this is the advantage of the Riesz gradient derivative in all space. But that's why I just want to introduce why now what happens when S goes to 1. The advantage of the Riesz fraction gradient is that, in fact, can also let S go to 1, and this goes smoothly in a certain sense from the non-local to the local problem. This is also the case for the Gallardo if you take this constant appropriated scale. As you know, this constant may depend singularly when S goes to 1. Okay, now the idea is a kind of stability with respect to this parameter, which has some interest, because that means that if you have a non-local diffusion process, it's a Levy process behind all this, in this diffusion equation, for S close to 1, it behaves close to the local problem. In fact, when you have, you can even do better. You can even take, and this is what I want also, take a variation of Vs, take also a sequence of Vs, comparing to V in L2 as well as, and this is weakly stable for this variational approach. Why? Because we have a priori estimates independent of S of the time derivative with our assumptions. That's why I take U0 now in H1, so it is in all HS0, so there's no problem. And also, there is also weak convergence of the fractional Riesz gradient. Why? Because there exists a uniform Poincare inequality with respect to S close to 1. And in fact, because of this, the energy estimate is also independent of S, so this gradient converges weakly to some vector in L2, which can be shown to be in particular by using a kind of arguments of this type, the limit, because if you take a function, fix a smooth function, it is not difficult to show that this ds converge in L2 in this case to the gradient of the function, and then since you have this a priori estimate, you can also prove this convergence quickly. By compactness, you have this stronger, and again, you have this convergence. And now the issue is to repeat adapting the arguments. In fact, as I told you, this is here this a priori estimate is a consequence of the, again, a priori this Poincare inequality is true near 1, is not true near 0. So cannot let sim go to 0 is a more delicate point. And of course, all the functions f and phi plus and minus, if they depend on s, they are uniformly bounded. So we can make this limit proceed, which means that in fact, in a certain sense, this is the sense that we can approach the local corresponding S1 limit case by non-local fractional problems. And this works not only for this gradient, but also for the Gallardo approach. The approach is a little bit different, but it also works provided you put the right constant that is singular when s goes to 1. So it compensates and goes to the limit. Well, okay. So again, the remark is similar. If you have non-degenerate assumption, remember this f related to the phi plus and phi minus, say f is large or is smaller corresponding to that non-degenerate assumption. In fact, the limit case has this property. I do not know, I'm not able to show non-degeneracy in the fractional case because the fractional Laplacian is non-local. So the argument for the local case uses the regularity of solution. In fact, the regularity solution says that basically when I have the equation, since the time derivative is L2 and Laplacian is also L2 when u is equal to v, also these terms are equal to time derivative v minus the Laplacian phi, almost everywhere. So that is why in the limit case you may have, under this assumption, non-degeneracy, also the quasi-characteristics are characteristics. And in this case, the convergence of the quasi-characteristics corresponding to the non-local problem converge now strongly because the limit function is a characteristic function. And this is a very simple observation that if you have a weak limit, you already have a weak limit. So if you have the weak limit, in fact, there is a simple interpretation of the convergence of the weak limit, which means basically this L1 norm converging to this area of this set. But on the other hand, you see that since this is smaller or equal than 1, if you square, it is below. So the limit sup is controlled by this. Of course, controls limit inf. And again, this converges weakly, so semi-continuity gives this, and this is the same because this is a characteristic function. When is 1, is square is 1, when is 0, square is 0, so it's the same. Any power of characteristic function is a characteristic function. And this means the convergence strong. Weak plus L2 convergence gives you strong convergence, which is a remark. So the remark here is interesting because this gives you a continuous dependence on this threshold V. So in this procedure, you can take this Vs depending also in this parameter of the convergence and taking the strong convergence in L2 Y. Because all the a priori estimates do not depend on V. The passage to the limit only takes into account the convergence of the quasi-characteristic functions, okay? But here again, the strong convergence of the V with the strong convergence of the US that exists by the a priori estimates are sufficient to go to the limit. So the argument is essentially the same to prove that the limit, weak limit, is in fact a quasi-characteristic function in this case from below. From above, the argument is also the same type. You don't take any open, and you just take again this convergence. You have a weak convergence, strong convergence, so it converges, and you identify the limit. And again, by this identification, you see that if this this must be so if this is positive, this is larger than this one, so this must be equal to this, and this must be 1, which is exactly what we need to show. Okay, I spoke about the stationary problem. In fact, this is a well-posed problem in the sense it is stable with time goes to infinity. Why? Well, first, what is the stationary problem? Stationary problem is being studied. In fact, I should say that this is a joint work with my PhD student that finished, Pedro Campos, you know him, with some previous results that I had before just for the local problem. But the stationary case is similarly stated. Local, no local makes no much difference, just functional framework changes. The approximation can be the same. You have also this a priori estimate. Now you have no time derivative because it's just a steady state problem. But you see the estimate is always the same type with epsilon here, now in the energy. And this, again, using now Poincare inequality, you see that for the L2 norm, of the difference for the approximated problem, now you use the approximated problem as a mean to converge, to use the convergence, because a priori we need to check how the convergence of the quasi-characteristic functions behave, but you can do this through the approximated problem. And if you just take this L2 difference in time of the approximated problem, you have a differential inequality just controlled with respect to the f. Of course, now I'm supposing that the v and the phi plus and minus are independent of time. Otherwise, it would be more complicated. I need to use some additional conversions of the v's, and I want to make this simple for this presentation. It's not impossible, but it should be much more complicated. So, but this approximation gives you a priori an estimate that gives basically using the usual trick by the approximation. So ut minus v infinity, the solution of the steady state, you introduce the approximations. These are controlled in epsilon, uniformly in time, as well as this one, and this one is controlled by the conversion of the f. So we can easily see that if this difference between t and t plus 1 tends to 0, we have that, in fact, they converge in L2 as time goes to infinity. And now we need just to make this machine working for the quasi-characteristic functions because they are bounded, they converge, you just need to identify the limits. And the identification is essentially done in the same way that I already explained before. Also, if the limit case, only the limit case is non-generate, so with the appropriated now associated to the stationary problem, the convergence of the quasi-characteristic function in time are strong for the characteristic functions in the steady state. Okay. In particular, this kind of weak the continuous dependence gives you the possibility and take more complicated problem. What is called quasi-variational two-phase problem, assuming that the threshold, this threshold is depending on the solution through some functional. So give any continuous operator from L2 into L2. So it's quite general. The compactness came from the a priori estimate, so don't need to say nothing about compactness of this nonlinear operator, just continuity is enough. And you replace the threshold V by this f of u.
You have 10 minutes this question.
Yes, I know. Okay, so I'm just going through. I will finish in 5 minutes. So, and this now can be done. I mean, the formulation is basically the same. You replace the v by this f of u, this functional u of the function itself. It is quasi-variational in the sense that it can be a variational interpretation of the problem for v, and depending the v on u, it makes quasi-variational. But this is basically by using Scholler fixed point theorem, because you notice that I have proved some stability of the problem with respect to the v. And then taking a w and solving the solution with w replaced in here, f du. So with v, with this fw, the a priori estimates work well and do not depend on the w. They are independent of this w. So there is an r, the inverse r depending only on the data, and then this becomes a completely continuous operator because the solution is also, well, I did not mention here, there is one more, estimate does not depend on W, which is type derivative, and then you have the compactness. But in any case, it is sufficient to be compact in this because you have this regularity in this combination of nonlinear mappings. So Scholar fixed point gives you an existence of a result. Examples: Nemitz operator, for instance, just a combination of some function, for instance, with some linear growth, for instance, continues in U, Nemitsky, or a kind of Urison operator. Or now we are approaching my objective, which depending, suppose that it is a couple system. So we have a system for U with the V that is given by some other equation. We give you a simple example with some kind of operator depending on U. This is just to give an example because my main is to come back to the beginning of my talk. Let's now take the reaction diffusion system, where now I can take this phi plus, phi minus, depending on U, and psi minus as well. And now the problem becomes coupled. So I want to solve this direct. Now I do not impose any conditions on this, except that this phi should be continuous in the argument. They should have linear growth so that I can have a priori estimates in this space that I'm working in, working space. And you see, this system now, I can use again the Scholar fixed point because I have a kind of dependence with respect to this threshold, okay? And since this V, or what I do is the following. I can decouple the problem by linearizing in the following way. I just take here U a W and V a Z, here a W, here a W, or no, the other way around. So the V is a Z and U is a W. So what I do is just take a Scholar fixed point in the following way. I define this mapping, a W and a Z in L2, and I take a solution corresponding exactly to freeze for the phi, the U by W and the V by Z, and the psi is the same, and as well, and this means that with this fixed point, again, a priori estimate gives you the conditions to apply the Scholar fixed point and get existence of solution. Okay, the uniqueness is another story. I'm not going to, of course, it depends much. In general, maybe non-unique. Again, in this case, you see, if I allow this linear growth of this phi size plus and minus, again, the non-generate case, taking now completely bounded by L2 function. I forget this phi0, I take phi0, 0. And again, that condition now, if I subtract this system, if U is equal to V, they disappear. I make the difference, F minus G, and I take the difference of the rest. And the difference of the rest can be estimated by this, and minus 2 phi0. So you see that now the non-generate case is not F, but is the difference of both F and G, that if this difference is not too large in a certain sense, into L2, and this is a minus here. There's a missing minus here. There's a minus here, sorry. There's a misprint, is a minus. You see again that the quasi-characteristic functions, in fact, they are characteristic functions, okay? And basically, this is the aim of my talk, to arrive here. I already talked about these possible generalizations, so I stop here. Thank you for your attention.